Johnson.
I'm John.
And we did our senior design project on exhaust pipe for Kohler Company.
A little bit of background, their old system, you can see in the picture here. Their original design, they had 3 sections here. The first one was a great big 10-inch pipe that came down. They had minimal travel with it. And the other one was a small, I think it was a 6-inch pipe that was just a flex hose that stretched all the way down for their smaller size generators. One problem they had with this was the end would rip and tear and wouldn't get very much of a life out of it, having to change the tops out all the time. They also had no quick connects for these, so each time they had to put a different nozzle on it for the different size generators and the different mufflers coming out. They said they could spend up to a day just trying to fabricate one, because for one, they didn't have no set place for steel, so they just had to try to find scrap steel to throw together just to try to make an attachment for this. They also had limited accessibility and limited maneuverability. This system has cables and winches attached to it, which would run over to a wall and then down, which were all operated by hand cranks. I think they had about 5 different hand cranks there they could try to adjust it with, and even with that they still got maybe 6 inches of travel, and they had no up and down height travel at all with it, and the only thing they could do with that would be the flex hose to get that with, but that didn't accommodate the large size generators.
And also the setup at Kohler is just basically just kind of archaic. It looks like it's from the 80s, and they just kind of want an improvement of what they currently have. Yeah. All right, and our design, Kohler wanted 6-foot swing radius, and we scaled that down to our actual model to accommodate that variable. And then they wanted 80 inches of vertical adjustment, which we actually did.
Yeah. 80 inches of vertical travel in a 15-foot room. It's approximately half the room. They wanted to adjust completely up and down, and we couldn't extend through the ceiling at all because their muffler was on top of their system there. So that limited us to keeping everything when it retracted, keeping it at that top level without going up any further than what it was. They also wanted a quick connect capability. They wanted to be able to completely change out the system within 30 minutes. They wanted it to be robust, handle temperatures up to 600 degrees Celsius because the operating temperatures of the exhaust of the generator are really high. Their current system, they said, would be glowing cherry red by the time they were done running, and they could run the generators, 24, 48 hours. They'd run nonstop for a really long time. They also wanted to have a max flow rate of 1,787 meters cubed per minute. That was, don't know how they for sure got that number. That's probably just their flow of their largest generator. Our system should accommodate that. We don't have any sharp bends, and with the round elbows, the exhaust should flow there without having a whole lot of turbulence.
And our whole design is made out of steel, so it will be able to handle those 600 degrees Celsius temperatures. The only thing that we have is you got to use lubricant in the valves, but you can just use high temp grease or something. Here's the design that we actually came up with. As you can see, there's the top flange coming down. This is the top. This is the bottom horizontal or vertical telescoping pipe sections rather, and then it'll come down, and this will actually be bolted to this other blue one, so that will squeeze the 2 sections together. And then so this bottom pipe is going to come up and around, and it'll rest on top of this, the top race of the bearing. And this is actually a thrust load bearing that we designed and made down in the machine shop here at Michigan Tech. We actually used a ball end mill to get this groove in that the balls ride in, and we have 48 balls or steel balls that are 5/16 inch diameter, and it rides really smooth, as you can see. This bearing, we couldn't find any to buy, so we decided to just design and build it. And I don't know if you actually implement this design, you will probably have to do the same thing we did, just because you will not be able to find a bearing that big for cheap. You could spend an arm and a leg on it, but it'd be a lot cheaper just to machine it yourself, which it's pretty easy to do as long as you have a CNC lathe. You just clamp it, set the zeros, The one thing is though, that, there's some burrs down in the groove itself, and that's just kinda, I just sand those out. Not really a big deal, but we kinda overcame that.
That was just from buildup on the ball end mill itself, just metal got built up in the grooves of the thing, and then it would reduce the surface finish of it. But since it's not a high-speed operation, you don't need a really great surface finish for the balls.
Exactly, and we kinda just packed them all in there. There's a little bit of gap between all of them, like, they're almost touching each of the balls individually, but to the point where they all ride smooth, as you can see.
Next part was telescoping pipes. Here you can just see the system's retracted. Here's extended out. To keep the model to scale, we went with a 45% scale. This bottom flange here bottom pipe is 4.5 inches, and it gets up to about, I think it's 5.5 inches is the top section. To assemble these, you need to start with the top section and go from the previous section and slide them in all the way down to the bottom one, which then you can weld this flange on. But to connect our design, since the tolerances were so tight, and initially rolling it created a V where you couldn't, the pieces turned out not to be completely round, created a V, so we just lined the V's up together to counteract that problem. And also with tight tolerances, we couldn't put a strip of metal, which you could use on the full-scale design with the bought pipes. So we just decided to use a V weld around there to create a stopper so the pipes could connect and hit together.
Yeah, so like John was saying, we used 18 gauge steel for the telescoping pipe sections themselves. The original design was to use 12 gauge, but the steel roller here at Michigan Tech was unable to roll those like we want them to. So we had two choices. We could either ordered pipe offline that was a diameter that we needed, but the thing with that is they would have been 1/2 inch increments going up. So you would have started with a 5.5 inch pipe and you would have ended with like say an 8.5 inch pipe, and that kind of that would have defeated our whole scale model system. So we just went with the 18 gauge and welded ourselves. When you actually implement this design, you're going to want to make flanges for where each of these have flanges on them that'll catch when you extend it all the way out. We just use a bead weld, like John said, which was acceptable for our design just because you can't machine
with the pipes not being round, there's no way we could have made a strip that would have actually fit. The only thing we could have tried to do was take a torch, heat it up, and try to bend it to shape, but for the time it's not worth it, and our system works fine without having to do that.
Alright, and here's it just shows, here's the maximum height that you wanted us to design around, and it can get up to this height, and then there's a bottom, and we decided to only go with four vertical sections just because the more vertical telescoping pipe sections you have, the less rigidity you have with them all the way extended down. So yeah, when you lower it, you're going to have a moment arm that's going to cause the whole thing to bend, but this will be resting on a generator anyways, so that's not really that big of an issue. The main thing is we got them to swivel, and we got them to swivel and telescope down, so we kind of we accomplished our goals of being able to do that, and yeah, all the criteria was met.
All the weight is on the cables itself, so with a little bit of weight resting on the generator would not cause any damage or hurt the system at all.
Alright, and here's our sketch of our proposed pulley system. That was just done kind of real quick in one of our classes, and it was kind of the basis of our design for our cable system. We knew we had to have 3 contact points coming down to that flange, and so you can see that in the drawing, well, one behind there, but yeah, we knew that we had to have the cables run up and go on top of the pipe, which if you actually implemented this into your facility, you're going to want to adapt your test cell room to be able to mount the pulleys, like not what we did here, but on the bottom or like off to the side on a support, so you can have the pulleys go and run down to the flange from the winch. Yeah, and you just need to make sure that you have all the cables rise up vertically at the same rate. So you're not gonna wanna have like, say, two pulleys come straight down, then one come off to the side. You can see that it's not gonna pull up on it evenly. So you could kind of play with that a little bit with speeds of winch, like the rate of speed that the winch retracts. But I don't know, that's something you need to figure out if you implemented this. And then here's a couple of pictures of our design in the build phase. You can see here we have just our horizontal sections all welded up. We did all the welding for the design in-house by me and John. It was our first time welding, so we actually learned a lot about that. And you can see it turned out pretty good. You just kind of see our layout here. And then this is just a picture of our station where we had all the parts. You can see all the individual components of our assembly there. And then the third picture here, you can see the arbor and the bushings that we made in-house. The arbor was used to mount the caster wheels up here. They're actually made out of rubber, so we didn't really have any way of machining them. Well, and they're on a swiveling caster, so we had to grind off the rivet holding them on and then slide the wheel out, then mount them on that caster. Well, you can't see the picture, but we put threads on that, so you put the caster on that and then just screw bolt on and then just mount it up in the lathe and turn down the groove, which worked pretty well. And yeah, it just worked for what we needed it to do. I'm pretty pleased with that.
You know, so you see too, before and after, that was before we took the sanding pad and the wear wheel to it. The metal pipe is stainless steel, that's why it's kind of got that different patina on the thing. And we welded it to, which was just a mild steel for the elbows. We went with mild steel because it was a whole lot cheaper than trying to buy a stainless steel one. Plus it was just easier to cut and machine.
Oh yeah, and also if you can see in the pipe itself, you got these real sharp bends going on. There's 4 of them, and I don't know if you can tell, but these are actually it's welded right here. And we could have ordered just like a cast steel elbow, but then it would have had flanges on it, and it wouldn't have had the tight bend radius that we have here. So our solution to that was we found a steel donut online that they actually use them for like exhaust systems on trucks, like to put stacks on. And so we have started a steel donut and we just cut it into 4 different quadrant or 4 different even sections and just welded them on the pipes, which worked very well actually. It saved us a ton of time and worked for what we needed them for.
Yeah, if we weren't going to use that or didn't get the chance to use that, we would have had to use chimney style, which was corrugated sections. We would have had it manually cut out, probably using the plasma table, roll them, and then weld them all together. Having a system like that would reduce your airflow, which could cause problems with or meeting the criteria for your max airflow with that. You have a nice smooth bend. You don't have to worry about hitting a crevice and creating any turbulence through there.
All right, here's our parts list of the model here. You can see we've got the welds laid out here. You can see where you can't read that, but there's actually a weld going on from the blue section here to the yellow, and then that gets bolted onto this other yellow flange here. And you can see that this pipe comes up. There's a flange here that rests on the top race of the bearing, and that's what lets it rotate, so it's like smoothly like that. And these are both identical joints right here, so we just made 2 of those. And you can also see that's a bushing, and then the bolts are not in this drawing, but you can just kind of see that as well as all the other different components. We'll send all the drawing files and everything to you. You could expect those soon.
Alright, we'll go to the
Okay.
prototype now.
And then we'll kind of show you how it works a little bit, like you can see what I'm playing with it.
Yeah, you can see the rotating sections and that worked flawlessly. One thing was originally we were going to only have 4 spacers here, but we found once these bolts tightened down, it squished it a little bit too much to get rid of the tolerance. So we would just have spacers be on every single bolt all the way around, and it fixes the problem of not being able to over tighten it. So with the lock washers and the flat washers, once you over tightened it with the spacer, it would get snug in that certain point, and you couldn't ever snug it too far past that, so you'd have a constant pressure all the way around.
And you asked us also to get the vertical movement, and we did that by just having, like we talked about earlier, these telescoping sections, and
Right.
yep, vertical. These drops and like you said, you're gonna have a problem with binding with these vertical sections, and that's kind of main thing is we actually got it to be able to go up and down and swivel around the whole moment arm. It's not a big problem just because you can have the end of the pipe rest on your generator.
Yeah. You can see doesn't take a whole lot of pressure to counteract that moment arm once it's sitting there. Main thing is just getting the tensions right on the cable, which figuring at that will have a lot to do with how you actually position the cables in the room itself. That can correct a lot of the problem. You can see how these pipes are still connected. The airflow through them is still solid. You're not going to have to worry about an air gap. Along with in each pipe is going to have an extension piece coming from the middle out to the next section of pipe. So there won't be any loss in these gaps. The airflow will keep traveling up through them and you won't have to worry about it coming out the sides, which will also have in each connection point here. Section will come in from the bottom and then extend up through, so your airflow will continue to be through the system.
So yeah, you asked us to make swiveling, telescoping exhaust pipe, and that's what we have right here. We're very proud of this design. See it going back up.
Some of the reason we have to hold it is partially because the weld, trying to get a weld all the way around there fluently was challenging with the thin material. If we had the thicker material, that would have made it a little bit easier. But we just mainly took the weld and went around. We had to add it in some spots where it was bowed out and decrease it in other spots where it was a lot thinner. Try to make a connection point all the way around it, which we did, and it worked. Also, to implement this system for you guys, we would have 4 connection points all the way around, which would help counteract the moment. Also, each cable itself would have its own operating winch. So doing that, you could adjust the tension of each cable individually, which also could completely correct any counterbalance there. Or you can have that system with tensioners. Each cable could have a tensioner close to the base. So when it was exited down, you could pull the tension and it would just counteract the moment if needed to. You might not even need to for the fact of just being able to lift the bottom and straightening the pipe.
Also, and as you can see here, as long as you have it all the way tracked up, you're not going to you can't notice that there is a moment arm going on it just because the tension of the cables makes it sit. And all these attachments here, we got them to kind of match up. They line up vertically, so it'll look nice on your ceiling.
We see with the telescoping pipes, that's the only way to get the requirements of having the 8 inches of travel. Before we had talked about using a flexo system, but you guys found that not to be ideal for what you wanted, for the fact of not having as long of a life as a full, robust, rigid system. But if you wanted to try to alleviate any issues with the telescoping pipe, you could switch to that. It would take a little bit more time and a little bit more development to attach to the bottom, but you can get rid of maybe just one section of telescoping pipe and implement a smaller section onto the bottom of that pipe with the different attachments if you would like to.
Alright, and some challenges that we faced during this design is, like we talked about earlier, the telescoping pipe sections, as you lower it down, they want to bind on each other. However, you can fix that just by resting the end of it on the generator. Like you can just rest on here, and then what else we got? Yeah, we had to machine those caster wheels, like we talked about earlier. Also, we just use an arbor. Worked pretty well, kind of straight sheeting rubber.
The telescoping pipes mating, we had to use weld, like we said before. We couldn't use strips we had originally planned on due to the pipes not being oblong. If you were just to buy the pipes in the step increments, you wouldn't have to worry about that issue. And you could just, more or less, machining a strip would be a whole lot better using a mill, and you just cut the inside out and then you cut the outside out right to shape. Plasma table would not be the best bet for that.
that it was pretty critical to have that depth be pretty accurate, and even after we did that, the grooves were a little big, so we machined these bushings over here to fit in between the flanges, and then when we actually were in the construction phase, when we got it all together, they worked pretty good. The bushings were a little short though, due to the fact that the groove was a little, it wasn't as deep as the design was, just because the accuracy of that specific ball end mill, it might have been dull or something. But to solve that, we put little spacers on top of the bushings and kind of ground the bushing down a little bit, and it fit well. Obviously, you can see it works, and
Also,
so yeah, we overcame that one.
thicknesses of the bearing races and the flanges itself, we use 1/4 inch steel, and that has its own variance of it, just based on who you get it from. It's not 1/4 inch straight across, so any gap, if all three of them are a little bit bigger than a 1/4 inch, that creates the gap, which is why we need to increase the spacers, the thickness of them.
Then also we try to think of how you'd actually mount this to the ceiling, or in our case, the base. We just welded a flange to the top of the bottom side of this square tubing, and then just welded another flange to the top of the biggest telescoping pipe section, and then just bolted them together, which worked pretty well.
Our design, our biggest telescopic section is about 5.5 inches. So implementing in Kohler's design, that would come out to be probably closer to 12 inches with the 4 stages of the telescoping pipe, which you need to get a different size muffler, but for the system to work and the requirements, that's what would need to be done. Also, we had a problem with our back pulleys breaking on the back of the winch system. After the cable goes over the wheel, it runs back and needs to turn down and head down to the winch. Originally, we had 3 pulleys on there that were only rated for 40 pounds. Once we applied pressure to it, it instantly snapped the pulleys. So we went from a 40-pound pulley to a 420-pound pulley, and those have been proficient, and they provide direction to swing side to side to adjust based on the cables, and give twisting motion, also needed for how the cables run down and twist to connect to the winch. Anything else?
We're good.
And here's the cost analysis total for this build, totaled about $874. That's including everything from the stand and the winch up to just the nuts and bolts on it. The most expensive individual item was a steel donut, which was well worth the cost for the design. Also, the winch, you can see here, that was a $50 winch. It's actually a really, really cheap winch and does more than what we need it for. The winch is for your full-scale system. 3,000-pound winch would probably more than justify, especially if you're going to have more than one. You could probably bump that down. You can get a winch for approximately $100, so 4 of them together, approximately $400, and you can have a full working system, and that feels is really cheap for the purpose it would serve.
And then, in conclusion, you asked us to build this prototype exhaust system. You wanted us to make it swivel, be very durable, robust, and to actually come up and down. And our proposed model here does everything you desired it to do. I mean, the problems with the moment arm, that'd be, well, like I said earlier, that'd be solved by you just resting it on the generator you're testing. And
if you were worried about resting it on a generator, it could be another project of working on just the cable system. That's kind of a full project in itself, of working on what you guys have to work with in the room. I know you had mentioned before the current pulley winch system, you had a steel structure mounted onto the wall, and that ripped off due to the forces of the cables. And also on your top ceiling, you have about 2x2 square foot where you can actually mount stuff to that you were using for your current design. That could be looked more into of seeing what you have available to mount cables and pulleys to. With that 2 foot, you could have your 4 cables on each corner mounting off of your eye hooks welded to the flange, and just more or less figuring out there how you're going to run the cables across the ceiling and what you're going to connect them to.
all right, any questions for us? And we will send you all our files that we have soon, so expect those. And thank you for this project. we learned a lot, and I don't know, I hope you like our design. We'll be in touch.
So my first question, you guys, like I said, I think that things have gone really well. I really like the rotating part. Is there, and I like how smooth the radii are as far as for improved airflow. Is there 10-inch donuts available, or did you look into that?
We did not look into that.
Well, yeah, the
I know
one,
they have bigger sizes, but I don't think they go that big.
no, they don't go that big. But you'd need to just make those in-house probably. I mean, with a 10-inch radius donut, the bend radius is gonna be bigger than that anyway, so.
We talked to Nick, and Nick thinks they hydroformed them is how they made the steel donut. Because originally we looked at it and it looked like the seam was solid all the way through, but once we cut them, it actually separated. So the steel donut separated in the inside seam, which we just had to close back up and weld.
See right here.
Yeah.
So it may be possible.
So yeah, they could, you know, if they wanted to, depending what they were willing to spend, they could get one made, make a mold for it, or they could just buy an elbow and cut the flange off.
Yeah, yeah, like it'd be too big to just get a, like bend it with a tube bender.
One thing, you know, going through this, and it's not so much of a question, it's more of just an observation, but it seems to me that you guys went to great lengths to make sure that your flow was not obstructed. Did that really complicate your design?
Not really, I mean,
It's just more tedious things to actually implement it and have the inside pieces here. They're most likely gonna have to be thin, and then it's just trying to get the welder down in there to weld around the gap and then make sure that's not gonna obstruct the thing. Because originally they wanted a 10-inch pipe from the bottom, and they didn't want it to be any bigger than 10 inches on the top, because they didn't want to have to get a new muffler, because that, they said maybe up to $20,000 to have to re-change the muffler on the top. And then it's mainly the paperwork trail of having to go through and get it approved.
yeah, and with these telescopic pipe sections, one goes up and then the other one sits below it, and then has to go up like that. And that was kind of our design, and it worked out to where you don't lose any, there's no exhaust leaks caused by that, because they're overlapping in the right direction.
Will your current design as it sits now, will that handle the 600C that it needs to?
We tried doing a flow analysis on, I think it was
What's
a
the
resin inventor, and we couldn't completely figure that out.
Okay.
1200 degrees? That would,
No, the flow.
oh, the flow.
No, temperature.
Oh, the temperature.
600
Oh, with the
C.
stainless steel, that's same system they have, so that should more than handle it.
Yeah.
Yeah, it's gonna get hot and it'll be glowing, but it'll last.
I guess this is one of those questions that I don't know, I always ask it. If you had to do it all over again, if you were gonna start from scratch, what would you do different?
We would use standard size piping for the telescoping
Outsource the
sections.
bends.
Yeah. Ben's having that steel donut saved a whole lot of time, saved a whole lot of messing around, and it just made it fluent. Because we just took the bandsaw, cut it in quarters, we set the edge up, and then just kind of eyeballed it and ran it straight down the edge, right down the center where it needed to be, flipped it, put it on the edge, and ran it. And I used a belt sander and laid it flat on the belt sander to make sure the end of it was flat, and did it on both sides. And then from there, I mounted this straight on the table with the elbow coming up, tacked it on all four corners, and then welded it in sections, so when the weld, it wouldn't twist it. And then to weld this next section was kind of a more challenge to make sure these were completely opposing each other. So I rested that flat on the table, set that up to raise it off the table, set this, no, I mounted this to the bottom of the table, clamped it, with this going straight up, and then I made sure that this was flat by using a level, put this resting on top of it, and then I took a straight edge, and I lined it up on both sides to make sure it was there, and then I tacked all four corners and then welded it around. And they both seemed to line up pretty well without having any twists there.
If I were to change something, I would not use these rubber caster wheels, because, I mean, we got swiveling ones, but we didn't need them to swivel. We welded
The
them,
main
we
thing
welded them to lock them in place.
we had the
So-
caster was, because we couldn't find a pulley that would offset off of the top of it. All pulleys are,
Yeah,
this
that's-
back one
that's-
are set in there, so we had to get something that was gonna have the wheel out past what's actually holding it,
Yeah,
without
we
having
should've-
something enclosed.
We could have just machined something for that.
did help for just lining the cables up. The main thing we had to do was get the eye hooks in place, and then try to get the wheel lined up, and then get it lined up with the back pulley.
So my next question, right, I like that you have a single winch to drive this thing up and down. You proposed that you'd have 4 winches, possibly 4 winches to raise and lower it so you can adjust the tensions. Do you see any potential issues with that?
The main thing is, making sure they can run together. If you can manually or control them all at once, that can help. But also if you were to adjust them individually, you need a way to get them back to its position where they're in sequence with each other. That's the main thing.
The syncing
Yeah.
problem?
Yeah, if Kohler has like an IT program, they could have them like make a program or something that, so you could have variable, retraction speeds for them if you needed to. But,
I also know with winches too, just how the cable wraps. The cable doesn't wrap fluently all the way around. If it starts wrapping over itself, that affects the speed of it because you have a bigger diameter, and it wraps slower it wraps faster having a bigger diameter when it's wrapping, and it extends faster too. So having a way to control the cable to make sure they're all in line with each other would be a issue. But that would be the best way to control it, to get it lined up. You can also have a marker maybe on the cables itself in different increments, so you can just see where it comes into the winch, and if you were to manually control it, extend it out before you go to retract it, you can move it back to a certain place, or you can just mark it. So take a piece of tape maybe, put it right there, so when you extend it out, you can just bring it back to just about the exact same place, because, you know, if you're off by a quarter of an inch, that really should make a difference.
My last question for you is, I really like how how you were able to make a system that allowed for the vertical height and swiveled so that you got all the different locations. And when you retracted it all out to get that vertical height, I saw that there may be a little bit of less rigidity. What, can't think of my question. How do you propose, or what would you suggest as far as improving the system to?
well, when we scale it up, you can actually have flanges in the telescoping pipes to rest on as opposed to our beads weld, which will help a lot in that it'll have, all of them will have equal, they'll take that, moment load all equally, and, well, more equal, more than what we have so far. And also, like we said, you'd be resting on the generator, take up some of the force there. And, one thing you could do, you could have just less, or like fewer telescoping sections, but longer. But the thing is, if you do that, you're gonna lose, your height when it's already all the way retracted. Like say this is like 5 inches lower, we could maybe have 3 sections instead of 4, which would increase the strength or the rigidity of it. But then again, you lose that vertical height.
No, I think that's good. I think that depending on how you adjust your system, you can get some benefits and